Good morning, boys and girls. I would like to talk for hopefully a 5-minute short video on inverting equations where you know the answer. Now you can see my slide up here, and there's me in the corner. Yes, so what we do is where we know the answer to something like porosity, for example, and also we've decided on the way that we're going to evaluate that parameter, porosity, for example. Let's say we're going to evaluate porosity from the density tool. We need to know the least certain variable, which is usually fluid density. So what we do is we turn the density porosity equation around, or whatever equation you're using around, to solve for the least certain variable, which is, let's say, rho fluid. And because wherever you have a bit of core porosity, you know what the answer is, right? You know the porosity is the core porosity. So you just put the core porosity in as an input, and you see what the equation requires you to have for rho fluid as the value that will, with a logged rho b and the grain density that you choose, whatever that is from the core or whatever, that collection of numbers will give you the core porosity, right? So that's the idea. So invert equations where you know the answer. Now normally, somewhere in the reservoir, you know the answer to things like, for example, saturation. You might have a bit of oil-based mud core, or you might have a bit of good capillary pressure data which you trust and you feel that is giving you the correct saturations. Or you might have a good 100% water zone where you know that the saturation is 100% and you can solve for M. So you can solve for lots of things by using this inversion method. It's very, very simple and very, very powerful and useful. As an example down here where I've just go through the example for rho fluid. So these dots represent levels where I've got a bit of core. So here we have a core porosity value, for example. That's a known value. And we have a rho b, which is a known value for rho b. Where's it gone? See it somewhere. Here it is over here, right? There's rho b, the red curve. And you use the density porosity equation and you solve it not for porosity, but you solve it for the rho fluid, which we call the apparent rho fluid. It's the rho fluid which is apparent from that equation and that core porosity which is given to it. And then we know that at that point, if we put in that apparent value for rho fluid with this rho b, we will get the core porosity. It's got to equal it, right? So we do that all the way down. We just put it in the batch file and we just calculate whenever we have core porosity is more than 0, we calculate the apparent rho fluid. And we can also do it for neutron. Wherever we know the porosity, we can see the apparent the neutron porosity fluid, apparent as well. So the APP is apparent rho fluid and neutron porosity fluid. And then we can maybe we can predict the rho fluid from maybe density neutron crossover, for example, from this thing here, or vshale or something. So once you've got the hard value, the apparent values, you can then try to predict them with some other logging curve. That's a very good way of doing. That's the best way I've found of doing porosity. The best way of doing matching core porosity. Now you can also do it with all of these things, at least these things, right? There's a little list of things you can do it with. You can do it also with the apparent salinity, right? In a water zone, if you know it's a water zone, you can work out the apparent salinity. Now that isn't a water zone, so that is not it's the apparent salinity if at SW equals 100, as we've talked about elsewhere. So you can do, once you get into this idea, basically wherever you know the answer to something, right? And wherever you're sure say you've got 5 wells in your reservoir, if you know that over that interval in that well, that is the answer for the unknown, like saturation or porosity or whatever, then you can use the equations that you use in your evaluation to reverse calculate the least certain variable, and then that's your least certain variable determined at that point, and you can relate that variable to other logs and predict it elsewhere where you don't know what that variable is. Okay, so it's a very powerful and very quick, and in my opinion often a better way of doing it than doing lots of work in the lab. For example, you can work out T2 cut, the cutoff for the NMR, by this method, which is a much better method, I think, than doing it in a lab. Here's some examples: row grain apparent, row fluid apparent, neutron porosity matrix apparent, neutron porosity fluid apparent, delta T matrix, delta T fluid, RW apparent. That's a very commonly used one. Most of us use RW apparent it's at some point in our evaluation. M apparent, BQV, the shaly sand input for Waxman-Smiths. We can get the apparent value of that from a known water zone as well. N apparent, if we know SW, we can work out what the apparent N is in order to get that SW. T2 cut, the T2 cutoff, the band fluid volume apparent, we can reverse calculate the band fluid volume apparent from that permeability. When we know the Timuir-Coates equation with its default inputs, we can work out what that corresponds to in terms of the band fluid and see if that's a way that we can predict that parameter. Porosity cutoff and SW cutoff for the cutoffs. So there's lots of, that is not all of them. There are many things. There's probably about, depending on what data you have, there's up to like 50 apparent values that you can determine at various places in your reservoir in different wells, and you can look at that as a reference for what that unknown input is elsewhere. Okay, please get into doing that, because that's a very simple and very powerful, once you've done it a few times, it's a very powerful way and very quick way, and as I've said, faster and cheaper than conventional deterministic laboratory methods, and you know the answer is right for the data and equations that you're using, unlike lab results. Okay, thanks folks, bye.